My name is Max Fomitchev-Zamilov. I'm the founder of Maximus Energy Corporation. I've been doing my own research at my home lab, primarily focusing on nuclear science. The first thing you see when you walk into our house is a germanium detector, high voltage power supplies, vacuum system, gas analyzers, particle size analyzers.
Did you say you had a nuclear reactor at your home?
Yes, I'm working on a nuclear reactor, yes.
How many hours did you spend studying, analyzing, measuring, and reporting on these vases?
At least 200 hours, maybe even 400 by now. I've developed this analytical technique that can help date archaeological artifacts. Whatever was used to make it was not a primitive tool or primitive technique.
All of this nonsense about these being able to be made with a stick and a rock is just garbage. It's just pure garbage.
With these hard stones, copper is useless, and you really need other stones to cut it. So I know, a lot of people who listen to this may say, oh, this is all bullshit and a pseudoscience. Well, it's pseudoscience unless you apply scientific technique to it, and then it becomes real science.
The museum stuff, we don't freaking know if that's real. And people are paying money and people are going to visit museums and going to look at objects that they think is ancient Egyptian, but is it?
And to give you an example, I spent a year on learning how to measure, actually more than a year, how to measure viscosity of crude oil. It took me that long to figure it out. And then I spent, another year or two, and I'm still learning how to measure neutrons and gammas. And I'm just getting started, with metrology. It's just, never-ending learning process. But that's only, one facet of what tells, I think, amateur apart from scientists. And we're talking about idealistic scientists because, scientists are people. Some are better than others, but, what I consider an ideal for a scientist. A scientist would always remain in doubt. And most people, when they measure something, they want to prove something. There is a certain point they want to prove, and that's the point they're invested in. And once you are invested in a certain point, you are very subjective about it. You want it to be true, and you will be upset if it is not so. And it's understandable because, let's say, if you're an entrepreneur and you're making a claim that your widget does something miraculous, of course you want that claim to be true, and you have no incentive to doubt yourself about it because then, you undermine your sales speech or your investor pitch. It's understandable. If you're an academic, then, your grants depend on the veracity of your claims. So you want to be correct, or you will not get, the next round of funding, may not get the next round of funding. But unfortunately, this partiality to the outcome detracts from the truth. And that was the reason, why I didn't go into academia once I realized that academic scientists, by far and large, are partial to their pet theories, pet ideas, pet whatever. Nobody's interested in truth anymore. And then, you become critical. Yeah, and in science, you have to be critical because that's kind of the scientific process. You are critical about everything and about your own thoughts and line of thinking in the first place. Because if you're critical, you can have the discussion and you can uncover truth. But if you're not critical, well, you're never going to uncover anything new. So in my mind, scientists needs to be critical endlessly, relentlessly. So whenever you get a good result, you never pat yourself on the back and say, oh, this is it, I've done it. So the first question you ask is how I could have gotten it in error. And you start digging and digging and digging. And after you dug long enough and didn't find a problem, then you can have a reasonable certainty that, perchance you could be right just this one time. And to illustrate this, with my own experience, in my recent work, I detected a flux of neutrons from my reactor, which was an Beall design. And it took me nearly a year to prove to myself that that flux was genuine. So I spent a year measuring the same thing over and over under different regimes and verifying different things about the data set I was capturing. It was, tedious and meticulous work, but that's, what you have to do in order to be sure. And few people have the stamina or, can stick long enough at it. And besides, what you're trying to do, you're trying to undermine your own achievement or your own discovery. And that's why a lot of, papers or reports that are written, they're not worth reading, is because a person is interested in a certain outcome, they achieve it, they describe it, and they publish it, be it in the form of a paper, a blog, or video, whatever. And there is a very limited, self-criticism, and that's what makes it of little value. Because if you have checked the obvious things or less obvious things, how do we know you're not mistaken?
Right. Yeah. So that search for truth is really what probably got you interested in this Vase topic.
I'm ultimately interested in the truth. I don't care what truth it is. I'm not vested in a particular outcome, but the search for truth makes it interesting to me. And the other thing I discovered about myself, and I didn't know that, I actually like measurements. I didn't know I would, but turns out I enjoy this, meticulous measurements and systematic errors control. And I think because there's beauty in it. Like art is beautiful, math is beautiful. Well, measurements are also beautiful if they're done right. And I see that. And I think that's why I enjoy measuring the same thing over and over again, because then it gets more and more perfect. Your errors go down and I see beauty in it.
Yeah. How many hours did you spend studying, analyzing, measuring, and reporting on these vases?
At least 200 hours, maybe even 400 by now. It really went fast because I got so interested in it. And literally, I would get up in the morning, and before I have my coffee and just wearing my boxers, I would run to the computer and rerun my MATLAB scripts to see what results I've gotten. And I was spending all time I had. At one point, I had four computers, crunching through the numbers in parallel, because it was taking sometimes a day or a day and a half to crunch this 3D scan, because it was just so high resolution. And I couldn't wait. So I had 4 computers crunching. Yeah, and a pretty good ones. One is like Core i9, latest and greatest, the fastest. I bought specifically very fast, the fastest laptop I could find to crunch the numbers. So it was supremely exciting, and I don't know why. I mean, some things are hard to explain. It just really hooked me. Well, I guess number crunching. I'm partial to number crunching. Yeah, I'm partial to measurements. It's kind of part of my DNA.
Did you say you had a nuclear reactor at your home?
Yes. I'm working on a nuclear reactor, yes.
That's pretty cool.
Yeah, I've published my results last May in Nature Scientific Report. So that's the neutron flux I mentioned. So that's, one of my interests.
Nice. What are the other instruments that you've got? Because you're working primarily from your home at this point.
Yes, working primarily from home. And then for a while, I thought about getting a space or renting or buying a space. And I almost did. But before I did, I realized, well, then I have to drive to work.
Yeah.
And I'm very fortunate to have a sweet, loving, and caring wife, Veronica Winters, who puts up with me, because she permitted me to turn our house basically into a lab. So the first thing you see when you walk into our house now is a germanium detector with a liquid nitrogen tank. So you stumble over that, and you get into the living room that has 2 big electron microscopes in it, and 2 smaller ones that I'm trying to repair. And then, so it's 4 electron microscopes at this moment. So the 5th one I sold, fortunately. And then you go to my lab, and another like 3 or 4 germanium detector, a 300-pound lead shield, that nuclear reactor I mentioned, high voltage power supplies, vacuum system, turbomolecular pump, all sorts of vacuum gauges, vacuum feedings, gas analyzers, particle size analyzers, gamma detectors, neutron detectors, and you go to my other rooms, and on every surface there is something in various stages of assembly, disassembly, repair, or disrepair, depending on on what I do. And sometimes I get carried away. If there is something cheap, I buy it, and then I realize, oh shit, I need to repair it. And then I start repairing it, and sometimes it doesn't go the way I want, but because I already paid money for it, I'm too cheap to throw it away. So Veronica told me, quit doing that stuff and focus more on research, and that's what I'm trying to switch towards, because I was really carried away with all of the repair and refurbishing work that I'm doing. But it's like your vases are your babies. This scientific equipment that I make and repair are my babies too. Once I bought it, I feel like, well, I need to restore it. And even though it was a tangent, now it's like a main road. And I do agree with her that I need to put some of that aside and make some more time for what I should really be doing.
Yeah. Makes sense. Yeah, cool. I'm excited to get into the, you spent, like you said, 200 to 400 hours studying these things. So you took a number of my vases, you took the scan reports, you spent a lot of time analyzing them. You created a scientific paper based on all of your analysis. I'm excited to dive deep into that and kind of share with the audience, all of the work that you put into it. But I met you through Ben Van Kerkwijk.
Yes.
Yeah, and so Ben came down here to work with you and to get some fragments scanned that are directly from the step pyramid of Dozier in Egypt, and so I want to talk about that. But Ben and Russ Allen came down to get those scanned, and I forget which episode that was, but we had a great chat in this room. But then you and I were able to connect from that visit, and
yeah, that was fortuitous.
It was, yeah, for sure. So do you want to talk maybe before we get into the report and the vases here that you've studied and analyzed? Maybe what were the key findings from the work that you did with Ben?
I would say the key finding was that there was nothing I would say remarkable about those shards, in the sense that when I proposed for Ben to bring them over, I was expecting to find bits and pieces of metal tools that were used to carve those. And earlier I mentioned that scientists shouldn't have like a pet idea, but the truth is, whenever we start a scientific investigation, there is always a hypothesis. So you start with a hypothesis, but you shouldn't be like too attached to it. So my hypothesis was that those, these metal stone vases were machined using metal tools, and because that's how we think of machining. You have a cutter or an end mill, and those are metal tools. So whenever you machine, tools ablate, and they lose bits and pieces of the metal that gets wedged into the stone, and under the electron microscope you should be able to see that. And that's what I was expecting to see. And when we looked, the samples were remarkably clean. They were the cleanest samples I've ever seen, and that really struck me, because in my line of research I use electron microscopy a lot. In nuclear science, I put my samples in it. And in my samples that come from my reactors or from my experiments, I find all sorts of stuff, like without trying, all sorts of metals, all sorts of contamination. And the thing for me is, because I've looked so much at various samples through electron microscope, I know they're always contaminated. So whenever somebody comes in and says, oh, we have this unobtainium on the sample, I always say it's a contamination. But when I looked at these chips that Ben brought, they were like pristine, as if they were cleaned by plasma. Like, how the heck is this possible? So I didn't find the smoking gun of bits and pieces of cutters or end mills. But we did find a few metallic inclusions, like a piece of iron, and those are small, like, micron size, and piece of titanium and something else I don't recall. But I cannot tell whether those are natural or artificial. One piece, did look like jagged, so it could have been like a chip, but I just don't have enough information. And that's another thing I would want to emphasize as we talk about, scientific method. So whenever you find something unusual, generally you cannot derive a conclusion about it until you do not just more studies, but your studies need to be comparative in nature. So that's why I was very keen on trying to get another chip from, let's say, this group in Russia, or from somebody who works with stone, to get a chip that is known, that has been machined, and we know what sort of tool was used to machine it. Was it like a steel tool, or maybe it was a copper tool? But we know what tool it was. And then, if I stick that under my SEM, I'll be able to establish a baseline. So I say, okay, well, you take granite, and that granite was cut, using copper saw with some emery in it. Well, that gives me a baseline of how much copper I would expect to see in that cut. Or if it's, another stone that's been machined using, a stainless steel or some carbon steel tool, that would give me a baseline. That particular stone machined this tool, how much metal should we expect? So once I have that baseline, I can do comparative analysis. I can look at another shard and say, does it have more or less? And does it have, the same or something different? So without having a baseline for comparison, it's very hard to pass a judgment. So that's why, in all honesty, I cannot derive any judgment about the samples that Ben brought, except that they were supremely clean, because there were no contaminants. And I find that unusual.
It is, yeah. And so I guess first question, what could naturally cause a metal like titanium or iron to be embedded into the stone?
Well, I'm not a geologist, so it might be that, if you just look at a random piece of granite, you can find an inclusion. So I just don't know. But that would be my guess, because, and that's another argument I'm having a lot with other people in nuclear science community, because there are a lot of people who are interested in low energy nuclear reactions or cold fusion, and they always claim transmutation. And transmutation means that a new metal or a new element appears where it should not be. And my argument to these people is, well, you forget that no metal is pure. So let's say you have an iron bar, and you think it's just iron, but it will contain nearly the entire periodic table in it, in some smaller fractions. But it will, because no material is pure. And in that bar of iron, there will be gold and silver. It will not be a lot, but, if you do something to it, that stuff tends to migrate. And that actually happened in my research. So I was working with a nickel alloy, and that nickel alloy was evaporating under the influence of X-rays in my reactor. And at the bottom of that pit, I was getting rare earth. And I was like, holy smokes, I'm synthesizing lanthanum and cerium and praseodymium out of nickel. So I was pretty excited, because an electron microscope was very clear. It was this pool of rare earth in otherwise your bulk nickel. So I even, submitted a paper to the conference. And then I reached out to manufacturer and asked them, what else is in your alloy? Because, when I looked at their spec sheet, it just said nickel and cobalt and maybe something else, and nothing about rare earth. But it had an asterisk that said, and other proprietary additives. So I said, what other proprietary additives? And they say, oh, by the way, we add some rare earth to it. And when I look at the boiling temperatures, sure enough, nickel boils before rare earth. So what I had in that pit where the X-rays were hitting the metal, nickel was evaporating, and the rest of the additives were concentrating. It was like, a mini refinery. So when I presented the paper, it was an example of how you can get fooled, because everything is a mixture of everything. So if you take a piece of granite, you'll find, uranium and thorium in it for sure, but you will also, find iron, and you might find, titanium and good knows what. So you need a control, and that's, a very well-known thing in science. You need to have a control and do a comparative analysis. So,
okay. So what could account for the cleanliness that you observed in these? Because these fragments were, according to Ben and Russ, they were found beneath the step pyramid. And so they've been sitting there since the step pyramid was sealed in 2650 BC, so 4,600 years ago. It's not as if people have been, rubbing, cleaning these things. They were placed there, they were left there, they were forgotten for thousands of years. What could cause that to look so clean?
Well, I have two ideas. And first of all, I would start by saying, I don't believe that, pyramids were, religious objects or religious, structures. I kind of find it funny when historians or archaeologists don't know what something is. They say, well,
ceremonial.
If it's a building, they say it's a shrine, right? Yeah. If it's a tool, they say it's a religious artifact. So by the same token, you walk into a metallurgical plant, you have no idea what it is. It will look damn impressive, pretty high beams and fire, and you say, well, of course it's a shrine. And all this, tweezers and hammers and something else, those will be, religious tools. So that's, I don't know, maybe because scientists tend to be atheists, not that I am an atheist, but, a more rational explanation is closer to me. So I'm thinking, those are, some utilitarian structures, and these are all, utilitarian tools that are not like magical artifacts. So it was used for something. And because I'm a scientist, I'm familiar with plasmas, and I'm familiar with sound. And the two things that are unique about sound and plasmas, they have pretty darn good cleaning effects. In fact, the way we do microchips, plasma etching and plasma cleaning is used all the time. It's like a go-to technological method for ensuring purity, getting rid of surface contaminants, stripping layers. It's plasma etching, plasma cleaning. So if you have a dirty vacuum chamber, you create some plasma and pump on it, and it's going to be clean. So plasma comes to mind, and sound. So we use ultrasonic cleaners. Sound just shakes stuff. And if you have anything on the surface and you shake it long enough, it's going to dislodge everything. So from the scientific perspective, I think you can achieve, the same level of cleanliness with plasma or with sound. I'm not saying, that's how those were cleaned, because, I don't know how dirty they were in the beginning. It's also possible that, I don't know, if they were like found in the desert, I would say, well, maybe just sand blowing, with just a blade and clean it. But because they were found in the pyramid, unless they were like in the desert before that for, several hundred years and sand and wind cleaned it, I don't see how else they could be. But, what do I know?
Yeah, fascinating. So, there's so many mysteries and so many unknowns about them, but yeah, there clearly could be some technology that we don't understand. What we don't find within them, embedded in them, or at least what we haven't found yet, is copper, right? So thoughts on that? That's the explanation currently, that on the inside of these things, copper tools were used to.
Yeah, that's personally a very interesting topic to me, and that's why I'm dying to get a piece of stone that was worked using copper, because I want to establish a baseline. So if somebody could cut me a piece of granite using a copper saw, I'd appreciate it. Even Veronica, my wife, volunteered, say, I'll cut it. If all it takes just, running the saw back and forth, I'll do it. So I might end up taking her up on that. But when I was watching the Scientists Against Myths video, when they had this Olga Vdovina made vases out of stone, one thing that I noticed, I don't think she used copper tools when she was making them. She used instead wood with some, I think, flint or stone attached to the wood. And she was using basically an equivalent of an emery in a mixture or slurry. And I was just grinding. So it was stone on a stick, so she used. And to polish the surface, she also used stones. So I think it's quite possible to make a vase like this in a general sense, in a general shape and form, using stone tools alone, and without resorting to any copper, because frankly, I don't see how copper would be any good, because she was even, drilling holes in the lugs with a wooden stick, basically, that was tipped with the stone. Because copper is just, too soft. Yes, so you need a stone. And if you use like copper for a holder, it's no better than a stick. And copper was expensive at the time, so stick is cheap, So I don't see copper as being, useful manufacturing material unless you're maybe working on limestone. Because limestone or marble is soft enough, it's basically chalk. It's slightly more, dense than chalk, and that you can cut with a copper saw. So that's where the copper saw would be beneficial, because you can actually cut it. Bronze saw would be better, but I think with copper you could. But with these hard stones, copper is useless, and you really need other stones to cut it, and to hold another stone, use a stick. So I think that explains, to me, at least, why we don't see much copper, or why we shouldn't be expecting to see much copper.
Mm-hmm. Yeah, my understanding on the copper thing is that the explanation from Egyptologists is that copper may have been used to core, just for the process of coring the hole, and it would be copper that was attached to a stick, and then they would have little pieces of quartz or some abrasive material that, as you twisted it, that would core a hole down the middle of it, and they were cored. I don't know by what they were cored, but the interesting part about that is, my understanding is that theory comes from a glyph that shows Egyptians from 1300 BC, around that time period, working on alabaster. And so, of course, alabaster is a much, much softer. These are 2,000 years older than that. These are hard stones. Alabaster is very soft. It's like the breccia that we showed that Olga was working on. Very, very soft, very, very easy to work with. So I'm with you. There's a lot of mysteries about the tools. I don't really feel like we really have any idea what tools were used or how they were used, but that is, again, this search for the truth that we're both so interested in finding out.
Yeah, and just adding real quick, you're quite right. So coring with copper tube, makes total sense. And in fact, the scientists against myth have shown that you can core granite with copper tubing, because it's not the copper that does the cutting, it's the emery or sand or quartz crystals they do. And copper is just a holder, and you just twist it, and quartz grinds on granite, and of course, you make a hole. So that makes sense. So perhaps, some of these vases, were cored in the same way. But then, they were polished and machined further. So whatever traces of that initial core is gone. So if there was any copper left on it, all that layer was removed. So there could be hope in, like, if you find an artifact where the core was broken off and the bottom wasn't quite, cleaned or machined or processed, to the final shape, I would expect to find something there. And that's why I'm interested in looking into these, various cuts, because you need to have a baseline.
Yeah, I still haven't heard a good explanation for how the walls were thinned out, how they were able to hollow out the interior after the initial core was drilled down. How do you widen the inside?
An excellent question. And when I watched Olga's videos,
she doesn't do it.
Right. Well, her vases aren't that well hollowed out. And I can see how you can hollow out them to some extent manually, but when you watch videos on YouTube now, how people make them, that's all done on a lathe. And on a lathe, you have just an L-shape, cutter that goes inside, and you hollow it out that way. So my contention would be to make like a really narrow wall. You can do it on a lathe. Manually, it would be difficult. I don't want to say impossible, because, triple axle was impossible until it was done, right? I'd say it would be difficult, but once again, everything is comparative. And when we get down to discussing my paper, I will present my reasoning for why I don't think it was done manually.
Yeah. Yeah, Olga, I thought, did a nice job hollowing out the soft stone, the breccia
Right.
that she had, but she didn't hollow the diorite
Right.
object that she was working on. And so you take a look at something like this, which is granite, which has a hole on the top that's the size, it's smaller than a penny. If you put a penny on here, it's not going to fall through. But it's all the way cut and up under to this part. You would have had to have some kind of a tool in there that was 90 degrees that you're spinning around, So what is that? Is that a rock?
It has to be a lace in my mind.
Yeah.
And you have to turn it, and you have to have an L-shaped cutter. Otherwise, I don't.
But what type of a cutter? I mean, they didn't have, would it be a copper cutter to cut granite?
Copper cutter is not going to do any good.
No.
You can machine granite with some types of carbon steel. I don't know how efficient necessarily it would be, but when I watch videos of other people making, granite artifacts, they typically use diamond tip saws. So they use diamond tip saws for cutters. And I think it's a pretty interesting technology because the object is turning, and then your cutter is a disc. It's also turning. So they use a turning cutter on the turning object, so double the speed, and that way they can machine the outer surface. And for the inner surfaces, I only saw them using the L-shaped steel cutters. So perchance you'll ruin your cutter in just one vase, but heck, if you have a bunch of them. So how it could be done in the past, I don't really know, but I don't want to say it was impossible to do any other way because
Right.
I don't think you can prove a negative.
Right. What else? Sorry. What else, if anything, from the work that you did with Ben jumps out prior to shifting to the work that you've done here?
Well,
Ben and Russ, I should say. Yeah.
I think Ben threatened to bring some other samples for me to look at, the one that were dirty in his own words, and I'm excited about that because I want to see what those contaminants are, what that sort of dirt, because I have a hypothesis too on how this could have been made, and I call it nuclear machining hypothesis. So suppose we entertain an idea that there were advanced civilizations, prior to ours, and I don't really understand why scientists don't like discussing this. Heck, we're discussing aliens. Why not discuss other civilization? What is so taboo about it? But if there was an advanced civilization, why are we so certain that they were using the same machining tools as we are using now? Because, we're using cutters and end mills and discs with, diamonds or quartz crystals on them. But I'm thinking if there was a really advanced civilization, they been more clever about it. And nuclear science comes to mind. And of course, because I'm a nuclear scientist, everything nuclear related is interesting. So I thought, what if they used some radioisotopes to machine this? Particularly, what is a radioisotope? Radioisotope is an element that emits high energy particles, be that, gamma rays or X-rays, or some radioisotopes emit alpha particles or electrons. And those particles travel at such a great speed that when they strike surface, they ablate it. And it's similar to ion beam machining that's used in microelectronics, nanoelectronics. So some electron microscopes come with ion beam tool, or you take your samples and you can direct that ion beam to shave layers off, and you can, make a gouge, you can peel a layer. So it's a very well-known machining technique. So why, maybe this advanced civilization used something similar, except could have been an ion beam or could have been, just a beam of particles emitted by a radioisotope. And then if you are that advanced, maybe you can synthesize enough of this, radioisotope to where you can machine something not microscopic, but, something that you can actually hold in your hand. And if that is the case, I should be able to find, markers of it. And that's why, I borrowed a couple of your vases and, analyzed them because, I'm hoping to find some markers of that, be that in the form of residual gamma spectra or in the form of decay products that are left there. But that's, what I'm thinking of. And I'm not saying, this is how they were made. It's a hypothesis I'm testing. And at the end of the day, I might able to say, well, I know I was wrong. This is not how it was made because I didn't find anything. But it's an interesting hair for me to chase.
Yeah, for sure. Yeah, so I mean, you were able to take two of the vases from my collection and look at them, and you were able to look at how many STL scan files, CT scan files?
22 from your collection.
22,
right.
Yeah.
22, and then we scanned 3 modern artifacts, and then we had 2 scans from Olga Vdovina's vases. So is it 27 altogether?
Yeah. So walk me through that process, and how did you start the process once you got the scans?
Yeah, well, first of all, I want to thank you for scanning all of those because that was a very high quality data set. And, science these days is about analyzing data. So you need lots of data to analyze. And the more data you have is better, and the higher quality data you have is even better. And I'm very grateful for you because you provided a large data set of very high quality data because we're talking about CAT scans, which are far more precise than optical scans.
And there's some debate about that, and not from me and not from you, but there's a couple of people that are out there saying that these laser scans, where you're just scanning the outside of the object, is the way to go with scanning stone vases, and it just doesn't seem like that could be further from the truth. Can you talk about the precision involved with these CT scans?
Right, and I'm not an expert on metrology, so take my words with a grain of salt. I just look at the data, and I will comment from the standpoint of the data. So the CAT scan has a lot more points in it. I would say 10 times, 20 times more. So if some vases that I analyzed, I had optical scans. So those took maybe a couple hours to crunch through. The vases that were scanned using CAT scanner took day and a half, sometimes 2 days, because there were just a lot more data points. So resolution, in terms of how many points per inch you get, is obviously one advantage. The other advantage is resolving capacity of the instrument. So the resolution in terms of how small of a feature you can see, and what's the certainty that you're seeing a small feature that is a true feature and not the artifact of imaging. And that's like a very important point that I want to dwell upon. So when let's say you take an optical scanner and you scan an object, I almost immediately will say that your scan is probably invalid because you're assuming the instrument behaves in a certain way. And in science, you can never make that assumption. And here's where calibration is important. And that's a point that I argue all the time, not just with amateurs, with scientists. Because let's say I make this neutron detector. Somebody buys a neutron detector from me. They make a measurement and they say, here. And I say, well, where is your calibration measurement? So, all right, I made a good instrument. I sold you a good instrument. But how do you know that at that moment in time, when you're taking this measurement that you're going to stake a claim on, that the instrument is actually working? Because, things happen. And it's like, it's like breathing. Everything breathes. Everything, goes in and out of tolerance, of calibration. Noise creeps in. Is just whenever you take an important measurement, the first thing you do, you take a calibration measurement. So in case of the neutron detector, you take a neutron source, you capture this spectrum, you make sure it looks the way it is, and then, you take your measurement, and that's how you know that the device worked. And then every once in a while you repeat this calibration, especially when the measurement is important. You want to make sure, is the instrument still working? Because they never do. And in the case of metrology, there are metrological standards. And that was the first thing that I did when we started this, I said, Matt, we need this metrological standard because I don't care what instrument it is and what the lab is telling about themselves. I want to see a scan of a metrological standard because that scan tells us two things: that the instrument is working, that's one thing, and it's also like a golden case to validate the analysis technique. Because if I take that scan and this metrological standard is a bead, it was a ruby bead, I think 2 millimeters diameter or something like that, so rather small, but it was scanned and I was given, this STL file. So I crunched that file through the same algorithm I crunched the vases, and I wanted to see, am I going to recover the stated diameter of the bead, which I did. And when I recover it, what will be, the difference between what I get and what was on the calibration certificate, and what was the actual measurement, and all of that, matched within the declared tolerances, and I, disclosed that in the paper. There was some deviation, and I used that deviation saying, okay, well, this is the limit of the resolving ability, which was worse than what the instrument could do, but that's the algorithm. You crunch numbers and there are rounding errors, and all of that adds up and you lose some precision. But without that standard, I didn't know if the instrument worked, and I didn't know if my method worked, because at the end of the day, you crunch your numbers long enough, all of those rounding errors add up, and you entirely lose definition. You entirely lose resolution. So you take a vase, you scan it. So I don't know how precise it is. So what you need to do, you need to scan a metrological standard, then scan the vase, and then scan metrological standards periodically, to make sure that, your thing stays in calibration. And that was, one of the things I discovered in some of the scans. Some of the CAT scans had artifacts in them, looked like ripples. And, when I look at it, I don't know whether it's like a genuine feature of the object, or whether it's like aliasing. We're all familiar with aliasing. When you watch a video, it becomes grainy, so that's aliasing. So was it aliasing or was it something else? So I talked to the technician, and yeah, sure enough, it was, one of those things. It wasn't a genuine feature, it was an artifact. But, because
It was.
Yeah, it was an artifact, yes. But it was, rather small, unimportant, so I could quit focusing on it. But because the metrological standard was scanned, I was sure, that the rest of the scans, were good and solid. And the resolving ability of CAD scanner is at least, 10 times better than optical instrument. And I'm not qualified to discuss, pros and cons and limitations of optical scanning, but it's pretty clear. You see more with X-rays, and you see, smaller features with X-rays. You get,
and you're seeing the inside.
Yeah, and you're seeing the
X-rays.
inside. That's
Right.
supremely important.
Yeah.
Because, one of the things I've done in my analysis, I added, the analysis of the inside, because we all agree it's far easier to work the outer surface, and you can fool maybe somebody by kind of like Olga Vdovina did by working on one of her vases meticulously. She achieved some remarkable precision, but she couldn't do, the same for the inner surface.
Yeah. One of the pros of the optical scan versus the CT scan is the cost.
Yes.
And it's much cheaper to do an optical scan than it is a CT scan. And
True.
And just talking with I've been connected with the CEO of EMS, the people that were doing the scans, and he said the same thing that you're saying, that doing the CT scan for these objects is the only way to go. It's going to get a much higher quality resolution scan. You're going to see the inside, and he could have steered me in the wrong direction. I could have done a lot more very quickly, if he was just interested in just trying to get as much business as possible. I would have shipped them, probably all of them, for how cheap it was to do the optical. But he didn't. And he's like, you really need to go this way. And so we did. So we went that way, and you analyzed 22 of these artifacts. And I guess I should just point out that out of the 80 or 82 total artifacts in the collection, it's about a dozen that seem to me to be extremely precise.
That stand out, yes.
Prior to you doing the work, but what was the process that you took to undertake the work initially?
Yeah, and before I answer, I would say, in my mind, the biggest drawback of CAT scanner is not so much the cost; it's not portable. So you cannot take it somewhere, right?
Right.
You have to send the artifact there. But it's
Yeah.
just a side note.
True.
But what I've done, I've taken the STL file, which is a 3D model, and because all of this, vases are round, I figured the easiest way to analyze them is to cut them like you would cut like sausage and produce this horizontal. If the vase is upright, you cut it across and you produce this round slices. And it's the easiest thing on Earth is to see how round those slices are and how concentric they are. Because, I spent some time thinking about, what quality metric, can you derive? Because that's, I think, where I really would like to start. So when you take a vase and you want to say it's a high quality or low quality, what exactly do you mean, right? So you need to clarify what do you mean by quality. And on where you start, you define this quality metric. So what it is that you deem high quality versus low quality. And when I was picking this quality metric, it also bears a lot on what you analyze. And let's say, this vase is smoothly polished. You can say, well, the quality of polishing, could be one of it. Or, there's a certain shape. You can say, well, the quality of following that shape could be the other. But these are not easy things to do. So to me, the easiest thing to do was, well, I see they're mostly round. So if I cut them and get the circles, I could see how round these circles are and how concentric they are. And this is how I define my quality metric. I say a high quality object would produce these highly round slices that are highly concentric. And a low quality object would produce slices that are not so round and they're not so well centered on one another. And that's, in a nutshell, it. I made it a little bit more elaborate than that in the sense that I also look at outer surface and at inner surface. So we have two sets of circles, the outer circles and the inner circles. And maybe I'm forgetting something else. But in a nutshell, that's it, yes.
Okay. Let's take a look at your report. Ryan, can you pull it up? So do you want to walk us through this?
Sure, yeah. So what we're looking here at a draft of paper that I submitted to the journal is called STAR, Science and Technology and Archaeology Research. So this paper is under review. I don't know whether it's going to be accepted or rejected, but I framed it as academically as I could. And basically here I say, look, I've developed this analytical technique that can help date archaeological artifacts. If the object is round, you can apply this technique to an object to determine the quality of fashioning. And because different cultures or different historic periods involve different tools, perchance you can establish that you will get this different quality figures for objects made in different times or by different cultures just because they use different fashioning or manufacturing techniques. And that's, the main thesis of the paper. And I say, here is the method. And by the way, I tested this method on Matt Beall's collection of vases, which was also supplemented by 3 modern vases and actually 5 modern vases, 3 that like gift shop type vases and 2 that were handmade, just to show that we can tell them apart.
And the modern ones were also stone, of course.
Yes.
Onyx.
Yes.
Onyx.
Yeah,
and
onyx, 2 onyx, and 1, I believe, was probably marble.
Marble.
2 were onyx. Yeah, so onyx is pretty hard. It's pretty close in hardness to granite. And when I watch videos on YouTube, I see people cutting onyx with carbon steel cutters. So it's evidently machinable, but it's about the same hardness as granite. It's as hard or not too much softer. Yeah, so maybe we can go. Yeah, well, here I just discussed the background. So in archaeological science, people classify vases all the time, and Petri classified them, and of course I mentioned the pioneering work by Adam Young and Ben van Kerkwijk, because this is how I learned about the subject. So I give them credit for discovering that some of these vases are finely made. And I say, okay, well, let me take a look at it. So here is the collection of Matt's vases that I classified: S for spinner, V just for general type vase, and B for bowl type vase. So 22 objects from his collection are listed here. Some granite, some porphyry, and maybe one basalt. Yeah, and so those are 3 modern vases that I bought on eBay, like for $15, 2 onyx and 1 marble. And below are the 2 vases that Olga Vdovina made out in Russia manually.
It is worth pointing out that the modern vases, I mean, of course, those weren't intended to come with handles, but none of the modern vases that anyone is working with or comparing to these ancient vases ever come with handles.
Right.
None of them ever do. So,
right.
So again, nice job trying for Olga.
Right.
And her ability to put a couple of handles on that. That's brescia on the right.
Yeah,
very soft.
And I want to add a point about handles. So handles bother me a lot because they make analysis difficult, and I will return to it. But when you make a vase, you don't need a handle. And some of these vases are so small, handle is useless. So the reason that there are handles there is puzzling. And besides, most of those handles weren't originally drilled. They were drilled later. So they're called lugs. And when I look at it, I say, well, I think those were like there to keep a vase in place somewhere. Like if I'm thinking about it as a machinery, maybe the vase was locked in place on those lugs, and so it wouldn't shift. But I don't think it was like a handle for carrying or for aesthetic purposes, because as modern work shows, you don't need a handle. It looks better without a handle. It's far more difficult to make it with a handle. So why, unless there was a technological reason for it?
And why are you so convinced that the handles were drilled later?
Because the holes are crooked, and I don't remember somebody, I'm citing information I heard from somebody else. Maybe it was in one of the Petri's writing, but somewhere I read that, there are plenty of this where handles weren't drilled through. And on every one I've seen, the holes just don't match the quality of the rest of it. It's, they're all pointing in different directions. They're crudely made.
A lot of times they are not aligned. That's very true. And there are several, even in this room now, that are not drilled with holes. So I think that's very possible as well. I'm on the fence about it, but I think it's
yeah. So my speculation is, handle is a latch type thing, and but we can so that's shows a STL scan of one of the vases, and it shows how I sliced it. So basically, it's organized upright for analysis, and I slice it horizontally.
And this one is dolerite, actually.
Right,
There's
dolerite.
Yeah.
Yeah, and I used MATLAB for my analysis. I used MATLAB and MatGeom library for slicing. Yeah, so if you slice it, you get this concentric slices, and some slices with a handle that I had to discard, and I'll explain later. But here I talk about quality metric. So I used a least squares fitting technique. So it's a common technique. It's a go-to technique in science. If you have a circle and you have points and you want to see how well those points fit on a circle, you use the least squares fitting technique. And what you get from it, so you get a radius and you get a center. That's the outcome of a least squares fitting. And you also get this root mean square error that tells you how well the line or the points fit the circle. So the smaller it is, the better the fit. So I measure the radius and the deviation from the center, and that's the calibration standard, the bead that the EMS was so kind. Yeah, thanks. Yes, to provide. So I ran it through the MATLAB code that I developed, and I was able to recover its stated radius within the error of 44/10,000ths of a millimeter, which is slightly worse than the resolving ability of the machine, but given the all of the rounding errors and stuff, it's only 2/10,000ths of an inch, and that's how precise my analysis is. I cannot see anything more precise than 2/1000ths of an inch. So
to 10,000.
2/10,000ths, yes, 2/10,000.
So 0.2
Yeah,
thousandths of an
0.2
inch.
thousandths, right. So if you get a number that's less, you still have to say, well, it's probably 0.2 because the algorithm is not resolving better. Yeah.
Sure. Yep.
And these are, a couple of vases. And that's, I'm just blown away. I'm sitting here at Matt's lounge, and I'm looking at these vases, and I look at them. They all look fine. When I eyeball them, it's very hard for me to tell that some are well-made and some aren't well-made. In fact, I'm looking at them now and I say, wow, I cannot believe that the analysis showed that this is well-made, but that one isn't. Because when I look at them, they look fine. So when you look at the model for a precise vase obviously looks better. It's more like symmetric, but it's not that much better. Still, when you have this rendering over an STL file, it's easier to see imperfections in shape because the colors are gone, the shading is uniform, and you can say, yeah, that's more symmetric than the other. But, those are just two examples of what I deem precise and imprecise. And here are the points that I get from scans. On top is the precise vase, at the bottom is not so precise. And I did have to exclude the lugs, the lug handles. And that's where I spend a lot of time on. Because when you cut through the handles, your slice is no longer circular, and your analysis, my analysis is invalidated. And when you approach the handle, the quality of machining gets worse because where that handle meets the vase, there is a ledge, and it's not that well, polished off. And initially, I was just, get rid of that manually, and then I started thinking, well, gee, here's a typical example of a selection effect. You look at a data point, you don't like it, you discard it. So I spent a lot of time automating this process, and I settled on an algorithm that worked like this. I discard every slice of an object. If the root mean square error is outside of the average by the factor of 2. And I repeated this process, I think, 2 or 3 times. And then that's uniform enough to where it gets rid of all of the slices through handles and some of the messed up slices along the top and along the bottom. And without human intervention on all the vases. So the algorithm is applying the same set of criteria on which slices to discard from the analysis without me having a say in it. So I can say it's pretty objective, and somebody can implement a different algorithm, but there is no selection error that arises from human factor. But that's what you need to do. You need to get rid of slices through handles and some slices along the lip because as it curves, and some slices at the bottom, because bottom is on some of these vases is not flat.
It's usually rounded. It's
rounded, right.
Intentionally rounded.
Here's another problem. So it's easy to analyze, more or less cylindrical objects, but it's not easy to analyze rounded objects with this method, because as object gets rounded, your slices become oblique, and oblique slices magnify errors disproportionately, kind of like shadows of a setting sun become elongated, and everything becomes grotesquely enlarged. So you get the same thing when you have a rounded bottom vase and you're cutting it obliquely. You just get noisy results, not because the vase is ill-made. It's just because the analysis is not suited for oblique cuts. So fortunately, this slice selection algorithm that I discussed in paper in depth takes care of that. So it discards all slices that are either noisy or going through handles. Yeah, we can go next. Oh, so this is a good scatter. The deviation from the center is the concentricity, right? So all this, I think this is for this vase that I'm holding. So the amazing part here is that the blue dots are the slices for the outer surface, and the red dots are the slices for the inner surface. And you see the horizontal axis is in thousandths of an inch. And what we see is that the centers of the outer circles are concentric to within 2/10,000ths of an inch. And outer surface has, inner surface has slightly larger scatter. And even, when you feel it to the finger, you see that the inner surface is not as well finished.
I was going to mention that the inner surface on that, you can feel the tool marks. The outer surface is completely polished and smooth, and so that's going to create more of a tighter deviation from perfectly round. But on the inner surface, when you've got grooves going around there, it's shocking to me that the inner surface is that precise, to be less than 1/10,000th to be around there. That 0.75 of a thousandth of an inch. That's incredible given the tool marks on the inside.
So what this tells me is whatever tool they used to do it, it was like perfectly rigid. And this thing, I assume it was rotated, because I don't see how else you could do it. So it was rotated like perfectly axially. So the tool is perfectly rigid and rotation is perfectly axial, like in a chuck of a modern lathe, to where even though you can feel it, but each slice is still perfectly concentric, better than 1/1000th of an inch. That was pretty amazing. And this is like the most precise vase in the collection, according to my analysis. So that was pretty mind-blowing to me. So what else is there? Yeah, so, and this is a less precise vase. It's the other vase that we saw that for comparison.
Right. It's right back there, the second one in the back. Yeah, very, very large. And
yeah, and you can see that the concentricity was all over the place. It's like 20,000ths, 40,000ths. It's almost 100 times worse, than for this. But visually you look at it, it doesn't look that different. But once you put this slices under the magnifying glass, you see. So the bottom plot there shows you kind of like if you shoot at the target, right? Where your bullets land. Those are the centers of all the inner and outer slices for the precise vase, and you can see they're pretty well aligned, like amazingly well aligned. Whereas for the other vase, they're not nearly as well aligned. Yeah, that's for the other vase. So you can see when they were machining the outer surface and the inner surface, there was a drift, like systematic drift in the tool.
So what are the blue and orange lines here?
So the blue line is the centers of the circles of the outer surface, and red is the centers of the circles of the inner surface. So when they were machining it, either the tool was turning or the bit was drifting, so there is systematic motion to it. And you can trace that motion because you got two lines. Whereas for this, there wasn't this systematic motion. So you got this just scatter. And that scatter, was so tightly picked, if you overlay it on top of it, it would be just a dot. Because, they were different scales. So this this is like 1/10 of an inch, right? And the other plot was, thousandths of an inch.
This is not in thousandths. This is in,
no,
that's 0.2 of an inch.
Yeah.
Wow. Okay.
So the drift here is, 1/10 of an inch. So compare that to 10,000. So it's 100 times worse in terms of precision.
Yeah, if you overlaid this on top of the other one, it's going to be 100 times bigger.
Right. Basically, yes.
Right. Mm-hmm. And so the drift here, does that indicate that it was done in one pass, potentially? Potentially,
yes. That's what it looks to me. But once again, I cannot be sure unless you analyze a bunch of them. And they can say, if you make this vases, this is the pattern that you get. But because there is a pattern, I tend to think that there was a path to it. And in all probability, you would get it even with a manual tool if you turn it manually. But
because if you reset the tool, you wouldn't. Correct me if this is wrong, but if you reset the tool, if you take the object off the tool and back on, or even probably if you change tool bits, then doesn't the line break apart?
It should break. Yes, it should break. Yeah, I see your logic. Yeah, so it's consistent with that idea. Yeah, so it was done in one pass without clear resetting of the tool because the line is unbroken. Yeah, what you see is systematic drift. So as you were, hollowing it out, you were just shifting. It's, when my lovely wife paints, sometimes when she paints something over and over, it tends to slide because, that's what happens to us. You think it's close, but you put a next stroke, but it's not quite at the same place. You put the next stroke and the thing drifts. And every so often she comes to me and say, curse this eye, I was painting for so long and now it's in a different place. And that's what we see here, it's just what happens. Yeah, it's another vase, just for example. The other vase, it's not quite as precise as this one, but it's still pretty amazing. So we have 6 10,000ths of an inch centering error for the outer surface and little worse than 1,000th of an inch for the inner surface. So it's on par, with this vase, but I would say maybe like 2 times worse, roughly.
All right. So far, we're just looking at the couple that we've looked at. It seems like there's 2 very distinct classes of artifacts.
Right. That was the main conclusion. So this is scatter plot. On the horizontal axis, we have, I believe, the vertical axis is the deviation from the center. It's the concentricity error. Yes, and the horizontal axis is the circularity error. So it's a 2-dimensional plot. We have circularity error horizontally and concentricity error vertically. And this is a logarithmic plot. Logarithmic means it's not linear, because if it was linear, we would have just 2 dots in it. And because if we had 2 dots, we cannot see the points to individual vases, I chose a logarithmic plot, and a lot of scientists do it when you have data that's very different in size. You cannot fit it like on one page comfortably. And I think this is good because green vases here are what I deem precise, and I'll explain why. And blue is what I deem imprecise. And you can see that the red dots are the vases that are made by Olga. They fall into the imprecise class, versus orange dots are the contemporary machine-made vases that fall in the precise class. And on this particular chart, I just show a broad grouping. That's out of all vases that I analyzed, just looking at these 2 particular subsets of quality metric, how concentric the slices are and how circular they are. You have 2 blobs, 2 distinct blobs. One is I call precise, and the other I call imprecise.
And these couple of questions maybe on this slide first. So all of the 3 orange ones that are in there are the modern vases.
Modern vases, yes.
Okay. Olga's are the red ones.
Yes.
And they're in there with the imprecise class. And it doesn't look like the 2 classes are very far away on this chart.
It doesn't, because it's a logarithmic.
Right. But they really are extraordinarily far apart.
Significantly far.
Just because of the way that you've scaled this page.
Right.
So if this whole page was on scale, you would have the ones on the top right would be 100 times farther away.
I would say 10 times.
10 times.
10
okay.
times, yes.
Okay. Gotcha.
And you can actually see it here from numbers. You see the center of the bottom ellipse is 1 on the left, and the center of the upper circle is 10. So that's how far apart they are.
Got it.
About 10 times.
Perfect.
And the same true about the horizontal axis.
And the blue and the green are both from
your collection.
From my collection, right? Yep. Okay, I'm with it.
So the next plot is just a summary of the quality metrics. So on the previous plot, there were like 2 subsets of the quality metrics. It's concentricity and circularity of the outer surface. So this particular chart is more of a comprehensive quality metric that also includes the inner surface. So it's concentricity and circularity of both inner and outer. And also the error of the, let's say, the inner surface relative to the outer surface. Because you can have both of them, perfectly. But if you hollowed out your vase incorrectly, then there will be an offset. Yeah, and of course, that's a telltale mark of a manual labor. When you hollow something out, how do you know where the center is? You eyeball it. So chances of you hollowing out something, let's say, was a 10 micron precision, and that's what, half a thousandth of an inch. It's 10, 12 microns. Chances of you doing that, next to nothing, right? And much less on a bunch of artifacts. So this particular plot includes, all of this consideration. So it magnifies the gap between quality classes even more. And this is where I draw the line. I just draw the line arbitrarily, say, the quality metric of 25 is of my choosing, the boundary between the precise versus imprecise class. And below that, all of the half of the vases that I analyzed from your collection, and one I'm holding here, and 3 of the modern artifacts. And above it, the other half of the vases from your collection and 2 of the handmade artifacts. And what this chart alone tells me is, according to the analysis method that I chose, half objects in your collection are perfectly consistent with handmade vases. Handmade vases by a good artisan that put in their time and hollowed out everything nicely and made it, smooth and polished, and it looks pretty to the eye. But the numbers clearly show it. It's not perfectly round, it's not perfectly concentric. It's hollowed out, not perfectly either. And those are, the Olga's vases, the 2 red bars are entirely consistent with the other blue bars. Yet, in this subset, we have these green bars, meaning very round slices, very highly concentric. The outer surface is highly concentric on the inner surface, which means it's been hollowed out nearly perfectly. And how you can do this, without using some kind of measurement tool, I have no idea. And those are consistent, with machining. The 3 orange vases are modern vases that we know were made on the lathe, because when you watch, these videos, they showcase this, Pakistani, Bangladeshi shops where it's a primitive lathe, but it's a mechanical lathe nonetheless, right? So it has a motor, has a chuck. So this thing goes into the chuck, and then, the drill bit or the tool bit is secured on a table, and they, move it by turning the knob, or sometimes actually they hold the cutter. So sometimes they hold the cutter and they still, get pretty decent quality. But not only these green bars are consistent with machining, they are somewhat better. And few of them, like V4 or V18, are like 10 times better than in quality than this, run-of-the-mill machined. Which means if they were machined with extraordinary care. Not just, quickly, we need to make a $10, give thing. You can hold the cutter by hand because no time to do it. But it was done, with some extreme care. But it's consistent with machining. I cannot say it was machined. I can say it's consistent with machining, and it's consistent with high-quality machining. I mean, if it was done some other way, perhaps. But that's all I can conclude from this analysis. What else do we have there?
So that's incredible. First off, so it says conclusively that those 11 artifacts were machined.
Well, I would say, proper way of phrasing it, the quality of their fashioning is consistent with machining. So I cannot say they were machined, but I would say the quality of fashioning is consistent with machining. Yes.
Yeah.
Whereas the other one is quality of fashioning is consistent with manual labor.
Right.
Yeah, and I think it's a defensible statement, given the data that I presented.
Absolutely. Could you make those ones in green with primitive hand tools?
I rather doubt that, because, that's not Olga's result. She tried, and her objective was to disprove.
Right.
And she tried very hard. And her bars are nowhere, was it 100 times worse?
Yeah.
Yeah, 100 times worse than V4 and V18.
Yeah.
So, based off this, it's not a very large sample.
25 on 100. Yeah, she's got one well above 100 there. Right. Yeah. So 50, 60 times worse.
50, 60 times worse, right. And she tried very hard. Yep. So based on this limited sample, I would say no, right?
Right.
Obviously, if you had 100 manual ones, you would have a better sample, but we had only 2.
Right. So I think it's fair to conclude that the precise objects were manufactured with, maybe not scientifically, but that they were manufactured with some type of a highly sophisticated machine or device.
Some advanced manufacturing. I would say it would fair to say whatever was used to make it was not a primitive tool or primitive technique. Definitely not a handheld tool.
You're not going like this with a stick and a rock.
Because you're not going to get to 12 microns with a stick on a rock. Yes,
No.
I don't think so. And you will not get the quality of inner, versus outer,
Right.
better. I couldn't resolve it basically.
Right.
It was aligned better than the resolving method of my, number crunching
Right.
ability that went, to the limitations of the scanner.
Yeah, yeah. And this is really where I think the people who have seen and held and been able to examine these things just even visually on some of them, it's very clear to see that they weren't made by some primitive method. I mean,
Right.
the wall thickness, the roundness, it's just too perfect. So that really leaves two possibilities, and the possibilities are they're either ancient with technology that we're not aware of, or they're modern, and they were manufactured in modern times with and they're modern forgeries.
Right. And that's, I kind of touch on that point obliquely in my paper. It's not my expertise to determine the veracity of an artifact. I have no idea how to examine the provenances and argue, this is real artifact or a forged one. But I make a point that you can use this technique to tell things apart. So,
Yeah.
you mentioned.
Yeah, what we have on these is we have a history that goes back to, in many cases, the 60s, the 50s, the 40s, where these objects are, where they've been found. Maybe and they've been certified and verified by independent experts as being genuine and authentically ancient to the best of their ability. Now we've got, that's basically what we have. We have a family in many cases that's either bought these or been given these, decades and decades and decades ago, and we've got an expert saying that they're real. And so this is now conclusively stating that these were manufactured, for me anyway, manufactured by some type of a machine or a device from ancient history that we don't understand. And so now, it's like, well, where do we go now? What do you do with that? So I want to get back to that point here in a bit as to kind of the conclusion. And I am, I'm actually, there's been so much demand. There's been so many people asking for these things, wanting replicas and 3D prints, and people started to 3D print these on their own and started to sell them, the few that I made public. And so I went ahead and started a website and said, hey guys, you want them, they're yours, go ahead and buy them. But I can't guarantee that these were made in ancient times, and so that's one thing that I want to just make clear to the audience, that this is where we are with this. We're exploring the truth. We don't know if these are ancient or if they're modern. We know that they weren't made. I'm very convinced, very highly convinced that these weren't made by hand. But I think that kind of supporting that mission of truth and attempting to find out, how were they made, where were they made, is critically important. And so that's why, they're out there for the enthusiast to be able to buy. But, if one day I find out, because we're able to conclusively prove through, whatever, OSL or whatever it is that proves that these were modern, I'm gonna be very, straightforward.
We'll take it up with them.
Yeah. I'm gonna be very straightforward and honest that we found that to be the case. I try to take every opportunity that I can be, especially because they're for sale, to let people know, I don't know, man, it's one or the other. They're not made by hand, but it's either an ancient tech or they were made in modern times. And so, that's kind of always been the question on these things. And it's like, how do we finally get to find out, on an individual by individual basis, because every one of them's different. Every one of them has a story. Every one of them has a history. And finding out at the individual artifact level, where were they made? How were they made? Those are the questions that I think from a searching for truth standpoint, we have to continuously and aggressively search for those answers.
I agree. So you're entirely right. So a skeptic looking at this chart would exactly say, just like you said, well, it proves, those were made on a lathe and therefore they're modern.
Yeah.
Or somebody else like Graham Hancock would argue the other point, saying, well,
Yeah.
it means there was another civilization before ours.
Right. And I hate to give the debunkers and the detractors the answer to the question that they're looking for, but all of this nonsense about these being able to be made with a stick and a rock is just garbage. It's just pure garbage. What they're eventually going to go to, what every detractor, just say no, negative person out there
let me correct a little bit what you just said.
Well, let me finish that one statement first. I think that every debunker and detractor is ultimately going to finally move to the argument that they're modern forgeries because most of them right now are still sitting on, well, these could have been made with primitive hand tools by ancient people. And again, for me, that is so highly unlikely that I think people will eventually migrate towards these are fake.
Right.
Yeah.
So I just want to clarify what you were saying.
Please.
Basically, in these ancient artifacts, ancient vases, there are two types, maybe more than two classes. If we get to analyze 100 of them, maybe we'll discover they fall. And that's kind of expounding on my hypothesis. I think if we analyze 100 or 200 or 1,000, we'll discover different clusters of quality. And I think we can use those to date or attribute the objects, because somebody was better, somebody was worse, somebody had more advanced tools. But because this analytical technique allows you to gauge the quality objectively, vases made by the same people or at a certain time would tend to cluster, and form specific blots on the 2D map, or specific heights on this, on this chart. So you'll be able to tell when it was made or by whom if you have more of this. But regardless, when you look at them, we see two distinct types. And some are consistent, with manual, and some are consistent with advanced technology. We just don't know whether those are, genuinely old or forgeries, like you're saying. But if you go to a museum and pick a vase, maybe it was made by a stick and hand. We just don't know, because eyeballing it is not enough. And I was so wrong by eyeballing your objects and were sure that it was precise or imprecise. But when you crunch the numbers don't lie. So you can use this technique to tell whether a particular artifact was made using hand tools or was made using some, advanced, machining techniques. That's, what the outcome of this paper is about. You can tell.
Right. Yeah, it's interesting. I mean, I do have, sets of high precision calipers that you don't completely need the STL just to know, it's very difficult to tell with your eyeball, of course, but to get a set of precision calipers and to measure the X and Y axis and see that, it's just 1,000th or 2 deviation between X and Y axis on the same, line of longitude, then that's a great way to be able to say, is this extraordinarily precise or not, prior to a scan. And of course the scan just confirms it. But then, taking it past that, I guess worth mentioning that out of the 80 plus artifacts in the entire collection, having used the calipers on every one of them, it does seem as if it's less than 2 dozen, it's probably 12.5 or so artifacts that we could consider to be highly, highly precise. So, I mean, you're talking about maybe a quarter, maybe 20%, maybe 25% of the total artifacts seem to be in that class of high precision.
Right. And you cannot put calipers on the inner surface.
Correct.
That's,
yeah.
And some of them, like Olga's vase had a very precise outer surface because she cheated a little bit.
She did cheat. Yeah. How did she cheat?
She used a modern potter's wheel that's supported by a ball bearing. So technically it's a precision instrument, an example of high technology. And it showed immediately because she was able to turn her vase and use the marker. So there's a picture actually of that to see if there was a deviation from, a bump, let's say, on the surface.
Right.
And then she would polish it away. But it's possible only if you have a ball bearing supported potter's wheel.
Did the ancient Egyptians have Sharpies?
Well, Sharpies, you can use chalk, but they didn't have ball bearings.
Right. No
So
ball
if she
bearings.
used just a wooden potter's wheel,
Yeah.
they would be play and run out,
Yeah.
and you wouldn't be able to determine, you wouldn't be able to rotate it as precise as you can on a ball bearing.
Right.
And
And the first known example of the potter's wheel in ancient Egypt was from the first and second dynasty. It wasn't pre-dynastic like these are.
that doesn't bother me. I mean, what bothers me is the ball bearing, right?
Yeah.
See, if you just have a hole with a stick through it, the run out on it is going to be huge.
Right.
So you will not have any kind of precise rotation.
Right.
So a Sharpie or a chalk or a pencil is not going to help you because it's just going to wobble.
Right. But even with cheating, Olga was still not able to get out of that imprecise class.
Right. Because her inner surface, wasn't precise, and her core wasn't precise. But if we use just the outer surface alone, I think her artifact would have made the precise class. If we just went and calipers on the outer surface alone, I think she would have made it.
Okay.
And that's what they kind of showed when they went to Pushkin Museum in Moscow and picked another vase that was Egyptian, but that was worse quality in terms of the outer surface because Egyptians didn't have a ball bearing potter's wheel. But yeah, based on that one criteria, she would have made so the cheating would have been successful.
Okay.
But because I supplemented the quality metric with the inner surface and how how perfectly it was scored out, it clearly doesn't fall into the same category. Yeah.
So what are we looking at here then? This is the dolerite vase, and then those are the lathe marks within the inside.
Yes, you're looking at an optical image, a high-resolution photograph of this dolerite vase, and you can see the markings on the inner surface that are consistent with lathing. To me, that's pretty clear. This vase has been turned on the inside because I'm not sure what else could leave these marks, but I'm no expert, so I don't pretend to draw a conclusion, but visual examination to me is consistent with lathe marks.
Yeah, flint will tell you it's a stick with a rock at the end of it, but of course that doesn't.
It's clear evidence of turning of some sort.
100%. This was turned by something, right?
And this is the most precise vase in your collection. The one with was 12 micron precision or better.
Right. But many of the artifacts have those lathe marks on the inside of them, or turn marks, whatever you want to call them. Most of the precise ones do have something that's similar to that.
Right. Even the vases that were polished on the inside, under sufficient magnification, you could still see similar marks that were not completely polished away. So, if I was in academia, or if someone was in academia, you could make a nice paper, like a separate study. You just take pictures of the inside of these vases, and you take pictures of the inside of vases that were turned on a lathe. You compare them, and you say, this is consistent with turning on a lathe. And you can take pictures of vases that were, handmade, like Olga's vase or maybe some other vases, and you can say, this is not consistent with that. And then that how you can also classify some of this and say, some were turned and some weren't.
Yeah, and I guess the difference between the manual, the hand argument versus this, what we're seeing here is it's the object that was turned, right? So the object would have been turned, the tool would have been stationary, and the tool would have just cut into the artifact as it was turned around. And
now that I'm looking at it, actually it's possible, given the CAT scan that you made, it's actually possible to unroll the inner surface into a sheet and extract the grooves.
Oh, we got to do that.
And see how it will take in a little bit of coding, but it's possible to do because the information is there. You just need to unroll the surface. And then you'll have a map and see how you'll be able to see if there is like a single groove, for example. Is there a single uninterrupted groove that's kind of like on a record player?
Right.
Or is there a series of them, or how it's possible to do that.
So that would be able to help us understand whether or not it's like a corkscrew,
right?
Whether it's like just horizontal tool marks, or whether it's connected and they're all going. From analyzing these and looking at these, and it's very difficult to tell just with the naked eye, but But my bet is that we're going to just see horizontal, that it's not going to be like done in one pass with a tool that was a spiral groove. And that's because a lot of times you see larger indentations on certain horizontal levels. And like you can see it on the right there with that big deep cut that was made right there. That circle goes all the way around in most cases. And so that would indicate that it's not a spiral groove, that it's actually a like that tool, as this thing was turning, that tool had more pressure applied to it at that specific horizontal spot.
Yeah, you're right. So superficially, it's consistent with manual control of the tool.
Yeah. Yeah. So, yeah, that's interesting. And then that kind of does it for the report, I guess, right? I mean,
yeah.
So amazing job, amazing
Thank
report.
you.
Yeah, really, really good. And we'll make it available on the link, and it's on your website. So,
Yes.
yeah, we'll link it to your website. And then I guess, Ryan, the last just couple of pages was kind of what we already talked about a bit. We've kind of covered this, and then the thing with Olga kind of showing where she cheated. I mean, she's using a marker. She's using there's the
that's the potter's wheel, which is a contemporary piece of technology because it's, as I said, it's ball bearing supported.
Right.
So if she wanted to be entirely true to her cause, her potter's wheel should have been consistent with what they used in ancient Egyptian time, meaning either clay based or wood based, stick supported as opposed to ball bearing, because that's how she was able to achieve the remarkable accuracy of her outer surface.
Right. But even, you mentioned chalk. Even if the Egyptians were using chalk and doing something similar to this, the chalk would wear down as the thing is being turned, so you really...
Well, I think what she was doing, she was marking the high spots. So she would turn it, mark the high spot, and then she would polish them away.
Yeah.
And then she repeated.
Right.
So it's like temporary marking.
Right. And at the top, on the top quadrant above the handles on the bottom image, those lines, they make it look really good, but those are just marker lines, right? That's just from a Sharpie.
Right.
Going around there. Yeah. It looks like, oh, wow, that's an amazing.
But this is how she achieved this remarkable precision of her outer surface.
Right.
But it doesn't mean it was achievable in ancient times, as I said, because there was no ball bearing supported turntable.
Right. And people just seem to glaze over that. The fact that
it's a very important detail.
It really is, yeah.
Ball bearing supported potter's wheel is a piece of high technology.
Right.
Because it's straight, so the table itself is straight and rigid, which if you do it out of wood, it will be all curved. If you do it out of clay, it will be curved. And, ball bearing, of course, that's a 20th century technology.
Right. Very good. Yeah, incredible, man. Really, really impressive work. Do you want to maybe just for the audience, I mean, we talked about it for the last 45 minutes or so, but do you want to just summarize the total?
Yes. So I would put the thesis of this work is this. I've developed a numerical analysis technique that is applicable to round or cylindrical artifacts. And it involves a 3D scan of this artifact that you slice into circular slices, and you determine how round and how concentric those slices are. And out of how round and how concentric those slices are, you build the quality metric. That's basically a sum of roundness and concentricity of outer and inner surfaces, and how these surfaces are concentric, between each other. So you add all of those up and you get a number. And once you have scans of a bunch of objects and you apply this algorithm to every one of them, you get a distribution. And it turned out that in objects that I analyzed, which were 22 objects from your collection, from Matt Bell's collection, 3 modern objects made on a lathe, and 2 manually made objects by Olga Vdovina, it turned out that they all fall into 2 very distinct categories, and I called them precise class and imprecise class. And imprecise class is entirely consistent with manual labor using stones and stick, and Olga Vdovina's vases fall squarely into that category. And 11 artifacts from your collection are consistent with machining technology as being turned on a lathe. So 3 modern artifacts fall into that category. And some of your vases, like this dolerite vase and one of the granite vases, and I are 10 times more precise in terms of this quality metric than the contemporary lathe-made, gift shop artifacts. Granted, gift shop artifacts aren't, the highest quality objects, so I will not say it's impossible to make it. Maybe with enough care by a good artist, you can achieve the same degree of quality. So who knows? But the conclusion is you can use this technique to classify these objects. I cannot say whether it's a modern forgery or genuine. All I can say is you can tell them apart. And then somebody else needs to argue, based on provenance or where these objects were found, if they were, genuine Egyptian artifact or a contemporary forgery. But either way, it's a useful technique. You're able to tell one from another. And also, if we apply, the same analysis to a piece from a museum collection, let's say, Petri collection or Cairo Museum or some other, British museum, and they fall into the precise category, it becomes harder to ignore the fact that maybe, we don't know something about ancient history because, the fashioning of this is inconsistent with manual labor. Therefore, either there was high technology available back then that we're not aware of, or they were not made by the people we think they were made. But regardless, I'm proud of the technique that I developed because I believe it can be applied to a broad range of artifacts, because different culture and different fashioning method would bear a different distinct mark. And let's say if you have 100 or 1,000 vases and you analyze them all, they will group into distinct categories in this quality space. And I expect objects made by the same people, objects made at the same time, to bunch together. Because if it's the same group of people were making, the quality would be consistent. Or as time goes, fashioning quality improves. So clearly, with time, we expect to see more and more precise objects appear as stoneworking improves, as new tools come in. So I think broadly for archaeological or scientific community, this technique could be used to help attribute and date objects. So especially, once we gather more information and we start seeing, what other islands of quality factors start to appear. And then when you have an unknown artifact, based on where it fits on the chart, you can say, oh, it was made probably by so-and-so in such and such, period in time. And I think this is where the true value of this method is, beyond just purely, Predynastic Egyptian stone vessels.
You're doing this because of curiosity and because you are searching for answers, because you were, just like I was, completely blown away by Ben van Kerkwick's work on this topic.
Correct.
I'm not compensating you for your work. I didn't compensate you for your work. I gave you these artifacts and in hopes that scientifically you could find some answers and find some truth to what's really, really going on here. So it's not as if, I'm compensating you to try to find some answer. I had no idea what you were going to find, and you didn't know what you were going to find. And you're not doing this for money. You're doing this because you want to know what the hell's going on here, right? So I think that's a point that is worth at least mentioning on the podcast, that you're doing this because you're fascinated by this topic and you want to learn more and you want to share that information with people.
Yes. So I believe that there is a problem with academic science that has been discussed recently, that when scientists become like a career scientists, they lose track.
Objectivity.
Of objectivity, of curiosity. Even Einstein said that get a cobbler's job, because a discovery is too much to expect from a scientist. So get a cobbler's job, and you can always pursue your passion, vocationally. And granted, it's not easy. It requires means, because scientific equipment is expensive. Time is expensive. But at the same time, when you're motivated by curiosity, you get somewhere. That's how I feel, and that's why I chose the path that I'm on, to where I work by myself. and I explore, the topics that interest me, regardless of, whether it's practical or useful. So I don't know what this is useful for, right? I just feel it's interesting.
Truth,
so
human history,
yes.
understanding our past and
Yes,
what our ancestors were capable
exactly.
of. Yeah.
Yeah, because a lot of things, we're taught or we hear, we take for granted, they don't make sense to me, and I refuse to buy them. And if I can formulate my own opinion, I might as well.
Yeah, love it. Cool. So, what do you see as next? I think you feel like your work on the paper is essentially
Right.
done. I mean, the incremental work is going to lead to probably small, increases in understanding or knowledge. So, because the sample size was relatively large. So where do you feel like you're going to take things next?
Yeah, there are several steps I would like to take that are, interesting. Directly continuing, this work that I've done, clearly looking at some of the other artifacts from museum collections would be very helpful. Specifically, I've heard that Adam Young and Karoli Polka went and scanned a bunch of artifacts and from the Petrie Museum. So I'd be very, very curious to run those scans through my software in MATLAB and see how these objects fare, how do they classify, which category they fit, or just going and scanning some of those objects is also a possibility. So I guess that's one of the things I would like to do to subject a larger set of objects from known collections, with unquestionable provenance, where everybody agrees when they were and how they were found and what archaeological context.
Well, there's a catch there, but before I mention that, have you reached out to Adam and?
I have reached out to Adam. Haven't heard much from him about that. Karoli, I think, is writing on his own paper, so I think he's going to maybe share stuff when he's done.
Okay.
Just wait patiently.
Yeah. But that would be cool. But to collaborate and to be able to run data and analyze those scans for sure.
Mm-hmm.
Those were light scans. They were optical.
Yes,
scans.
they were using optical.
Yeah.
Scanner.
But even so, that's valuable information. We'll learn something from that. But I was shocked to learn that in a lot of cases the museum pieces we're operating under a false assumption that those have impeccable provenance in many cases. A lot of times those were donated by collectors and the provenance is unknown. It's not as if the museum pieces themselves have this incredible provenance and that they have known dig sites in many, if not most cases. I'm not sure which specific artifacts have that known provenance and which don't, but in many cases these were donated by collectors, and it's no different than what we're looking at here. And people, and that's why I'm so interested in getting to the bottom of this. In large part, it's because the museum stuff, we don't freaking know if that's real. And people are paying money and people are going to visit museums and going to look at objects that they think is ancient Egyptian, but is it? It's like, if this isn't real, maybe that stuff's not real either.
Yeah, and that's why I'm excited about this methodology that I developed. It allows classifying objects, and then it's up to the researchers to decide what to make of the classification, because that's the job of classification, to bunch objects together in groups. And then, archaeologists would come in and say, okay, well, this group means this group means that. And then, you know how to date and attribute stuff, and also, sort out the forgeries. But continuing kind of on this line of thought, what really, I think, made me interested in the vases, ancient technology aside, is the nuclear aspect to it. Because I'm a nuclear scientist, I have a nuclear reactor at my home. And when I learned about these artifacts, I thought, well, maybe, assuming this was some unknown ancient technology, why not? We all like sci-fi. We can fantasize that there was some Atlantean alien, I don't really care. It's unimportant. But what is important is, if there was a high civilization, they probably didn't use cutters and chisels, the same tools we think of when we fashion something. And creative people thought, well, what if they were molding this somehow, this technology where the stone was softened, and then you can mold it, maybe stamp it like it was plastic. Well, that's a great idea, right? So how do we test for it? I don't know. But the idea that came to my head is, what if they used nuclear machining technology using radioisotopes? And then radioisotopes would either strip layers of stone like ion beams do in modern microelectronics equipment, or perchance maybe these let's say beta particles. When you saturate a material with beta particles, maybe material becomes more pliable and becomes more fluid, and then you can use ordinary cutter to shape it, but it's no longer hard rock. It's now like a semi-plastic thing because it's like saturated with electrons, basically. So those are the two hypotheses that I found extremely interesting because of my personal interest in nuclear science. And that's why I borrowed a couple of your vases, and I stuck them in my germanium detector, and maybe we can see a picture of it. Yeah, so that's a massive 1.5 ton lead shield that I used to screen the object from background radiation. And below it, you see a dewar with liquid nitrogen. And on below is a picture of one of Matt's vases inside that lead shield, and that piece is sitting on top of the germanium detector. So that germanium detector is submerged partly in that liquid nitrogen dewar for cooling. And then I was capturing gamma spectrum from it. We're surrounded by background radiation. Everything on this planet emits gammas or X-rays at some minuscule level, but there is a signature of it anyway. And you can tell one rock from another rock by looking at its gamma spectrum. And if we scroll down, we'll see, so those are the two vases that I mentioned. And I got a couple samples of rocks, and those are the spectra that I captured. So I wanted to see if...
Of the vases?
Of the vases, right. If I just registered the emission, the invisible rays that these vases emit, would it look remarkable? Would there be anything unusual about it? And this is a spectrum, and it has peaks. And peaks are definite energies that mean something, to geologists or to nuclear scientists. But when I, let's say, captured a spectrum of one of the vases, of the dolerite vase, I didn't know what it should look like. So what I did, I bought a dolerite rock off eBay, mineral collector's item. And I took a spectrum of that rock also, and I superimposed one on top of another. And I see they're consistent.
They are consistent?
They are consistent,
okay.
Yes. So there are no new peaks. All peaks are the same, which was a little bit of a bummer.
Are they both on this chart?
Yes.
Okay.
The red peaks are from the rock, and the blue peaks are from the vase.
Uh-huh.
So you see all peaks match. There's some of a slightly different height, which means the rock had more of some minerals, maybe some uranium and some thorium and some bismuth than the vase, but nonetheless, it's the same composition. And if we scroll down a little bit, there is another chart. Yeah, that's for the other one. That's for the red granite.
Uh-huh.
Yes, and they're also more or less the same. So, and I bought a piece of Aswan granite from eBay also to compare. That's the kind of point I was making throughout this talk. All scientific analysis is comparative. So if you take a spectrum of anything, very rarely you can say if it's remarkable or not unless you can contrast it against something else. And in this case, I was contrasting the spectrum of the vase against the spectrum of the rock. And my hope was that if the vase was machined using nuclear technique, there would be trace radioactivity from those isotopes used that I'll be able to detect. Well, so far I haven't detected it. But I'm very interested in looking at some of the other vases in your collection, particularly at the basalt vases, because who knows, maybe I'll spot something there. But that's not it in the sense, does the nuclear analysis stop here? Because chances are, if the nuclear machining technique was used, the isotopes used would be short-lived, meaning they would decay in 6 months, in a few years. So assuming that these artifacts are ancient, none of those would be present because of the half-life. It will be all, pretty much decayed to background, so you wouldn't expect to find anything. So But in this case, it's possible to look for decay products. And decay products will be bismuth or lead or some other elements. Basically, for every radioactive isotope that we know of, there is a very well-known decay chain with lead or bismuth or something else of that sort at the end. So if I subject, let's say, these vases to microanalysis using XRF, which is an X-ray fluorescence technique, or microanalysis using energy dispersive spectroscopy and an electron microscope, perhaps I can detect traces of the elements that could have been the decay products of those radioactive isotopes used for nuclear machining. And that would prove the hypothesis. The challenge, however, is in the shape of these artifacts. You see, both XRF and EDS microanalysis techniques work, I want to say best, but I should probably say primarily, if not exclusively, on flat objects. Because the way it works, so here is your sample. Then you have a beam, be that electron beam or X-ray beam, and that beam reflects, and you have a detector at the side. So the configuration is specific. You have your beam here, you have your detector here, and this surface is expected to be flat. And when it works that way, the data that you capture in the detector will tell you what elements are present there. And you can say, okay, well, I got 1% lead, 90% iron, and 7% silicon, something like that. But if your object is curved, or if your object like a vase, obviously you want to look on the inside, and it's like deep inside. It's impossible to shoot a beam in there to where it reflects back and hits the detector. Right. And if you start messing with the geometry, and I tried that, because I'm a tinker, if a standard book approach doesn't work, you tweak it. And what happens is you mess with the geometry. Like I have an X-ray, portable X-ray gun, like a small one. I was shining it inside, one of your pots, and I was holding a detector to a side so it could capture some of the radiation that was coming in from the inside. But when that happens, because the beam bounces all over inside the pot, the entire pot glows. And then part of that radiation strikes the detector and strikes the gun, and you pick up all the metals that are present in vicinity, all the metals that the detector is made of, all the metals that the gun is made of. And you don't know what to think of your result, because it's no longer this spot that you were trying to measure. It's like everything because of the geometry. And I haven't figured out a way to overcome it except to maybe shift from trying to look at the complete object to look at pieces and at shards. And maybe with some luck, either I can get some flatter partial pieces from you, or Ben Van Kerkwijk was threatening to give me a few pieces for analysis. So maybe I'll be able to spot something there. But at either rate, this technique involves getting the electron microscope operational, which is something I'm working on right now. So I bought a new electron microscope, finer from the other ones I've owned. But the way it goes, a new electron microscope is $250,000. I cannot afford that, so I have to buy a broken, decommissioned piece of equipment, fix it, and it takes a while, and it's a precision piece of machinery, so you cannot just fix it. So you need to call tech support, and you need to get professional help and calibrating everything, make sure everything is working to where the results of the microanalysis are trustworthy. So that's a difficult part. It's easy to make things work poorly. You get to that point quickly, right? But here, we're doing science, and we want to look at, minute, contaminants, trace elements. So it takes an effort to get instrument to that level. But, I'm on my way, so I have a call scheduled with tech support, and hopefully with their help, I'll be able to get microanalysis on my microscope working. Then I'll be in a good position to, working with a great degree of certainty. Then I'll be in a good position to study, flat objects, and maybe I'll discover some contaminants, or maybe not. But I'm also, as I said, I'm also interested in picking up, a couple more artifacts from you and maybe studying them in that gamma detector. See, maybe there will be some radiation there too.
As long as you bring them back, we're good.
Yes,
Yep.
yes. In one piece, an important qualification.
Yeah, exactly. Right.
But this is, I guess, the most exciting part to me. When I read research about, Egyptian temples and Egyptian pyramids and sarcophagi and sites, I find very little mention of radiation studies. And this is, what I'm very interested and capable of doing. I have portable spectrometers, let's say, that I can take, and I can collect radiation background, and I can see whether, let's say, a sarcophagus or something else, has an unusual, signature to it. And all of that, could be recorded and analyzed. And it's also possible to do superficial microanalysis in situ, to where you have like a portable XRF gun that you can put, let's say, to a granite block or to a stone or to a chip that you find on the ground, collect all of that information, analyze later, and look for anomalies. And that's, what I'm, very interested in doing, given an opportunity. Basically go on site and collect some radiological data on site that may not support the nuclear machine hypothesis. Who knows? I must be prepared to give up my pet theory, but who knows, maybe I'll find something else. There was also something new I recently learned, which blew my mind. That everybody knows that, carbon dating is not 100% reliable, because there are cosmic events that happen regularly, like supernova explosions that send a bunch of radiation towards Earth, and that greatly changes, the balance of radiocarbon in atmosphere.
For a brief period of time?
Yeah, for a brief period of time. And I was reading a scientific paper on this subject where a geologist / nuclear scientist was arguing that a number of such events took place, and he was able to corroborate, those conclusions by looking at the surface of some of the rocks. And I didn't know this, but it turns out that, when this radiation hits Earth, it generates enough charged particles that not only, change the isotope ratio for radiocarbon, but they also leave marks on the surface of stones. And he was able to tell, which rocks that were exposed, to this sudden flux of radiation changed and how they were changed. Yeah, and I didn't know that was possible, so it blew my mind, and I became very interested in studying the effects of radiation on the surface. Evidently, there is a great body of work there already, so people know what happens to the surface. And I could just, learn this technique and start applying it, to your artifacts or some other artifacts that we find, see if there is anything on the surface, this, micro features, would be consistent with anomalous flux of radiation. For example, this basalt artifacts that you have, or basalt artifacts at Petri Museum, they all look to me like they were exposed to some extreme heat. And of course, we know extreme heat happens in nuclear reactors, but it also happens in other places. So I'm not saying it's of nuclear origin, but if it was of nuclear origin, you would see plenty of evidence of it on the surface. And this is something I wasn't aware of until like 2 weeks ago, when I came across this paper and I said, Degna, but that's, interesting subject to research. And that's, what you can use the electron microscope for, and maybe, some other techniques, but I need to do a lot of learning, because this is new. But, that's what makes it exciting, because, who knows, it would be interesting to be able to discover new technology that was lost in the past, or just having, the quest for this new technology to advance our knowledge. Because I think that's what happens when you follow your curiosity. You never know what you learn in the moment, how it forms a whole picture, later in the process in some, mysterious way. And I guess that's what makes it exciting.
Yeah, for sure. Wow, that's fascinating. So I just learned a lot. Thank you. So if a supernova were to occur, and the radiation that comes from the supernova would would hit the earth and leave an imprint on stone, and so it would leave an imprint on stone artifacts such as this. We're able to see that, and
Yes.
we can measure that.
Yeah.
And but if the stone hadn't been cut and quarried and turned into an artifact like this, then it's likely not going to leave the imprint on the surface of something like this.
I see where you're going with this. Yeah.
Right.
Could be a dating.
It could be a way to date
or
them.
assist in dating.
Yeah, for sure.
Because supernova events are recorded.
Yeah.
And as I said, there is a bunch of scientific literature on the topic, and it's not a controversial topic. We know that cosmic events occur, and we know they change radiocarbon balance in atmosphere. I didn't know that the rocks are impacted. That was new information. But if the rocks are impacted, then
we ought to be able to we ought to be able to study them and understand. We ought to be able to understand how many of those types of events each of these have been through, and if they've never been through one, or if they've been, then they're probably modern reproductions. Right?
Or let's say you go to a Sirion, right? It's made out of granite, and if you can detect this cosmic events on the walls, you can say, well, it's got to be a lot older than what were said.
Right. Well, we could date known stone objects and artifacts from throughout history, and be able to understand based on the surface and studying the surface of those, and having known when they were created and when they were cut and quarried and carved. We ought to be able to pretty accurately probably determine how many of those types of events each of those have been through based on what point in time they've been created.
Correct. Yes.
And then that could help us with dating stuff like this.
Yes.
So with the optically stimulated luminescence, it really right now only works on granite, and so that could be a way to potentially figure it out for all types of stone objects.
You've got to remind me about that too, because I forgot to look into it. I forgot the term.
Okay. Yeah. It's a new way, and it's not really out there in use yet, but it's a new way to date granite.
Yeah, that would be amazing if we learned how to date.
Yeah.
Even just granite, that could answer already a lot of questions.
Right. So what makes you think that that it's a real possibility that nuclear that this nuclear machine hypothesis could be something that ancient people had used at some point in time, or what are your thoughts on that?
Well, I have two thoughts on this, and I'm glad you asked the question again, because I remembered something. So first of all, we primarily use chemical energy right now. Gas, diesel, natural gas is chemical energy. We do use a great deal of nuclear energy also for power generation, power plants, aircraft carriers, things like that. And the more civilization becomes power hungry, I think it's unavoidable. We're going to resort more and more to nuclear energy. And that's why right now there is this fusion craze. Because I think wrongfully conventional nuclear energy has been deemed bad. I don't agree with that at all. But regardless, the reason everybody in scientific community believes that the nuclear energy is our future is because there is 1,000,000 times more energy density per volume or per unit of mass in let's say nuclear power than in chemical power. And if you have a civilization that's anywhere higher than we are, that's what they ought to be using, or something even more advanced that we cannot even think of.
Right.
But clearly they were not burning wood or coal.
Right.
And most likely they're not using cutters like we're using now, because if you've mastered nuclear technology, you need just 1 gram of fuel to fuel your car for your life, and you need a microgram of nuclear fuel to machine anything and cut through anything. That's why I think it's plausible. The other thing where I think it's plausible, few people know this, but this is a very well-known fact. There is a natural nuclear reactor that's been discovered in Africa, I think in the 60s. I believe in Gabon, and it's called Oklo Natural nuclear reactor. And the way it was discovered was a French mining site where they were mining uranium. And the uranium was shipped back to France, and it's analyzed isotopically because, when uranium is coming from the ground, it's ordinary unenriched uranium. Most of it is not suitable for power generation. Only uranium-235 is, but it's a minor constituent, and that's what refining or enrichment is about. So when French were analyzing the ore, they couldn't find uranium-235. And like, what the heck? So the alarm bells started coming on because they thought somebody was stealing, weapons-grade material, because this ore must contain known amount of uranium-235, and it wasn't. So they conducted an investigation, and much to their shock, determined that the uranium in that site is different from uranium that's found everywhere else. So uranium everywhere else on the planet has a very well established ratio of uranium-238 to 235. But not this site. In this site, it's depleted on 235 and otherwise enriched in 238. So the only explanation that they could come up with that a nuclear reactor must have formed naturally and operated for many thousands of years, burning away all of this uranium-235 until it was gone. And when I hear this statement, to me, it sounds as ridiculous as you walk throughout the desert and you find a perfectly formed Mercedes-Benz that formed there naturally. So that's the same, degree of ridiculousness to me, because it's very difficult to maintain, chain reaction for any meaningful period of time, because they are saying, well, the circumstances were there just right, where water was coming in and coming out, and this sustained, this chain reaction for thousands of years. Right. I just don't believe it. It's because it took Oak Ridge, Tennessee, a bunch of national labs figuring out how to maintain chain reaction, how to synthesize these isotopes, how to build the reactor, how to maintain it. So it took hundreds of PhDs and millions of man-hours of engineering, and we're building this, complex contraptions. And the difficulty there is, so you have this radioactive material, and if the reactor is tuned wrong, there will be no reaction. And if it's like over-tuned, it will explode. So you're basically trying to balance this nuclear explosion on the razor edge, where it's seeping energy. And by seeping, I mean megawatts or gigawatts, not like a multi-terawatt explosion, right? But if you tune it the other way, the reaction dies off. And if it goes the other way, you have a Chernobyl. So it's very difficult to keep it, operating in this very narrow range where neutrons are produced in just right amount. They're not absorbed, that when each neutron strikes a uranium-235, it shatters and it produces more neutrons. That's what the chain reaction is. So for that to have occur naturally by chance, all right, well, maybe once, but sustained for thousands of years to where all of that radioisotope burned out is just beyond credulity. So to me, it's far easier to believe that what we found was a remnant of an ancient nuclear power plant. That's for me easier to believe. It's less a stretch to assume that there was a civilization who, mastered nuclear power and exploited it, and now gone, than, just saying, well, it occurred naturally. Because, I tried different things in my lab on purpose and nothing happens. Well, granted, I haven't tried, for a billion of years, but still, this argument that if monkey, types on a typewriter and it will produce, Leo Tolstoy's War and Peace, is flawed. It's a common argument that we hear sometimes that, given enough monkey, enough typewriters, you get it. But, mathematicians and statisticians proved that will not take, all the time in universe for monkeys to type up, Shakespeare or something else. Things just don't happen. So, that's why I think it's plausible. And so there are some other things in Gabon also, like there is an airfield that basically Germans used, and currently still used by the government. It's just been extended, and nobody knows, who's built it. They were just, blocks arranged in the shape of an airfield, and which was large enough to be an airfield, and they just extended it. They just paid a little bit of more, but nobody knows, where it came to be, who built it, or why, because it doesn't look like a temple. It looks like an airfield, and that's what it's used for now. And it's not far, from Oklo. So, it doesn't prove anything. Of course, I'm speculating, but to me, it's easier to believe, this version of events, because it makes sense to me as a rational being, as an engineer, as a scientist, that, we're not alone in the universe. So we're probably not, the first intelligent beings in this world. It would be, too much for us to think that we are the only ones, or we are the first ones. There is too much self-aggrandization in that statement. So to me, it's, I think George Lucas's picture of the world makes sense. There are many intelligent beings. They all do something, so we are one of them. If we find the works of their technology, of course, they will look strange to us. Of course, we'll try to find an explanation for it, but I think it's time, we consider that as a possibility, especially in view of the development of technology now that, we use Space Webb Telescope to look for traces of other civilizations. So I think this is not, too far-fetched.
That's fascinating. That sounds like I need to do a podcast on this topic.
Probably.
Yeah, and probably get a guest in here. You said this is in France, or is this in Africa?
In Africa. It's Oklo.
And so, do we know anything else about it? Do we know when it was potentially in use?
They say, billions of years ago.
Billions of years.
Yeah, but we need to take it with a grain of salt, because it's their best explanation that for it to deplete all of its uranium, it should have been operating as a natural reactor, for billions of years. Another explanation could have been it's been like a conventional power plant, like a few thousand years ago, that just, burnt all of its fuel.
Right.
Or maybe it's a fuel dump, who knows?
Right.
So they just picked a model that would explain it, that went along with, understanding of geology.
Wow.
But, you can pick another model, and I don't pretend to be an expert on nuclear reactors of that type.
Yeah.
So...
but highly, highly unlikely.
Yeah, based on what I know and what it goes into building. I mean, look at Iran. They've been, trying to produce a weapon for how long?
Yeah.
And they couldn't, despite their best efforts. It's difficult. And, it took all of America's intellectual capacity organized, under Oppenheimer and a bunch of national labs to do all of it, and hundreds of PhDs, thousands of people, and it's a difficult process to maintain. It's very, for the chain reaction inside the reactor, it's very easy either to turn into explosion and destroy the reactor, or not go at all. So it will either fizzle out or blow. Just keeping it going, that's where the real trick is. And having it going for thousands or hundreds of thousands or millions of years is just beyond credulity. It's just...
and this couldn't be something that the Germans or that nobody was doing in the 40s.
It was found underground, so it's ancient. I don't think it's a few thousand years old. That's
right.
So
I mean, possibilities for what this could be then. I mean, it could be some ancient civilization was mining this uranium. Could it be that some life that came from some other place, maybe billions of years ago, got here and seeded the earth with life and said, well, how the hell do we get home? Let's find some uranium and start mining this stuff. And what are the options for what this could be?
Funny that you mention it, because I'm actually writing a book about this. It's a fictional book, but it kind of summarizes my thinking about it, because we know a lot about Sumerians. We know some about Egyptians. We are fascinated with this, ancient alien theories. So I decided to put all of that into fiction. How I think, the events would unfold. So about a few months ago, I started writing a book that I called Order and Chaos. And it's about a race of extraterrestrials that live on a wandering planet. And we know that, such planets exist. And I think their planet got caught on an orbit around our star, around sun. And they became, captives of the solar system for a short period of time. And in fact, there is evidence of it. And it's been recently publicized in astronomical publications a lot, search for Planet X. Because, comets and asteroids in the solar system are organized in groups. And that organization is consistent with another planet going, sweeping through the solar system and clearing the path. And that orbit is consistent with a planet that has been captured temporarily. Well, scientists think there's still a planet there they call Planet X they're looking for. It might be. My thinking is there was this passing planet was captured temporarily and was orbiting sun for an extended period of time. And I think the intelligent beings from that planet visited our world and established a base here for a while and left us with some of this inexplicable artifacts that we find. So maybe, that nuclear reactor, if it was indeed a nuclear reactor, is there doing, or maybe some of the structures, ancient structures or pyramids is there doing. Maybe they are the gods that created humanity. But that's, what my book is about. That's what I expound upon. That's what I speculate, that they were stuck here and their job was to unplug their planet, from the tug of the sun and be on their way because it wasn't good for them, to orbit. It was a free-floating planet. It's never meant to orbit anything. And its orbiting the sun caused all sort of, disruption out there. So they were stuck here in the solar system and on Earth, trying to be done with it. And in the process, they might have created us. They might have been, the gods we talk about in mythology or in holy scriptures. But I believe, they left now because, they are succeeded at their mission. They saved themselves and they're gone. And that's, what I write my book about. And it's called Order and Chaos. And I created a website for it, orderandchaosbook.com. And I'm going to upload chapters there as I finish them. But it might take me, a year to write it. But the vision of it all kind of came spontaneously right before I started doing this. Yes. Not much there. I just posted the prologue, but I have a few more chapters that I'm going to add. Yes.
Cool.
But
Ryan will be all into it, man. Ryan is our sci-fi guy.
Yeah, I wrote a little bit of it before. I guess I started this project, and maybe that's why this project, was Vases and became so fascinating because somehow it chimed with what I was thinking. And this Egyptian history is right there. And they have this winged disc. What else could it be? I don't think it's sun. I think it's this mysterious visitor that was orbiting us for a while.
Yeah, that's cool. You are from Russia.
Yes.
You came over to the U.S. in 1997. We were talking at lunch a little bit about some of the incredible stonework that exists in St. Petersburg,
correct,
in Russia, and I wanted to maybe see if you wanted to share a little bit about
Sure.
your knowledge on that, because I was pretty blown away. I didn't know about it. I don't think there's a lot of I don't think there's a lot of content out there on YouTube
Yes.
that's really looking at Russia for ancient civilization and for just potentially some inexplicable type structures and rocks. What fascinates you about that, some of that architecture? And
Well, I'm glad you brought it up. There are actually more mysteries to Russia that are known about in the West. So I'll start with the obvious, with St. Petersburg. So we're taught that it's not a very old city. Peter the Great built it. Yet when you visit there, you are instantly struck with the amount of megalithic stonework. And I'm not talking, just the granite casing of the Neva River. I'm talking about megalithic columns of St. Isaac Cathedral, some obelisks, megalithic vases, megalithic fountains, and the so-called Grom stone. That's the statue of Peter the Great stands upon.
How do you spell that?
In Russia, it's Grom, and it means thunder. Yeah, that's the rock.
Yeah.
So according to the official history, this rock was brought, and that's just like few thousand tons. This is a huge rock. It's like a miniature mountain. So the official history is telling us it was brought from Karelia, some 500 miles away, hauled through swamps without roads to St. Petersburg. And I'm thinking, if Catherine the Great or whoever commissioned it, they were surely not that stupid to order such a job. Obviously, the legend was written to aggrandize, the Tsar and Russia by attributing, this feat to them. The Empress commanded and the rock was brought. But it's just, a stupid undertaking that I can never, believe it being done. In modern days, that would be difficult, and, much less 300 years ago. So some peasants with horses and bare feet, 500 miles through Karelia and rocks and swamps, really, I just don't believe it.
And how much does it weigh?
Several thousand tons.
Oh my God.
Yeah, it's just, and there are many things like that, and they're like in front of your face, but because you hear this official history all the time, you never doubt it until you're supposed to think. So there is a substantial community of Russian amateur historians, archaeologists that look into St. Petersburg anomalies, that in St. Isaac Cathedral anomalies, because it's got huge columns, granite columns that are also like hundreds of tons each. So how would you transport them? And the question why is because you had unlimited funds and you wanted to spend all of your funds on making these huge columns when you had the rest of the cathedral to finish. But also what stains credulity is Winter Palace and the other palaces there. The first floor is buried. So St. Petersburg is built on the swamp. So why would you bury the first floor along with all of the ornaments there and then make a makeshift entry between the first and second floors? That makes no sense. Yeah. So you cannot even see the first floor. You can see just the little circles of what's left of it. But if you excavate, you see the columns going down. So the entire first floor is buried. Yeah, you just see little tiny semicircles. It doesn't make any sense. And there are a lot of towns like that in Russia where the first floor is underground entirely, like all over the place. So, what happened that we're not told.
Stone.
Yeah. Stone buildings, yes. So, it's consistent with Delage in recent time, but it's not mentioned like in any book. What happened that so much mud was deposited so quickly to everybody had to dig inside? But it gets even more interesting than that. If you go towards Siberia, you find mega earthworks, all sorts of earthen walls and dikes. And in Siberia itself, the taiga, the woods, it's crisscrossed in patches that are bold, devoid of forest, but it's squares. It's even squares as if, somebody just lined through the woods. And its step is about a mile. It's not exactly a mile, but, it's close. And somehow woods don't grow there. So there's something done to the ground to where, this grid remains. So it's unclear who's done it, why such an effort, how it's possible. And it just, keeps going. And it's like right in your face. And people now are researching it and asking questions. And I'm glad that this is happening because, there is just so much more out there that doesn't fit the narrative. But we don't know what it is. And what are we to research if not that? Shouldn't, science research what is really interesting, what is really exciting, what everybody wants to know answers for? And that's, one of those things that my father-in-law taught me when I was defending my dissertation. He said, dissertation needs to be boring. People must be asleep when you read it. Because if they're excited and they wake up, you're not going, to get your PhD.
You're right.
And I, didn't believe him, but I followed his advice. But, when I moved to America and I considered pursuing a scientific career, of course, I wanted to work on exciting stuff. So writing exciting papers, and I learned very quickly you cannot get those published because my father-in-law was right. Science needs to be boring. But, who needs boring science? What public good is in boring stuff? So we need exciting stuff. We need science that answers interesting questions, that, gives us something practical. So I know, a lot of people who listen to this may say, oh, this is all bullshit and a pseudoscience. Well, it's pseudoscience unless you apply scientific technique to it, and then it becomes real science. Of course, if you...
I think open-mindedly asking questions and expressing curiosity is not pseudoscience. It's just pure, it's science.
Right.
That's what we should be doing.
Yeah, so I think we should be applying, the best we know, the scientific method to all of these questions and getting the answer. If Peter the Great built it, all right, great. But, we could be a bit more critical about just accepting, what the textbooks tell us, when we... Oh, there is another example. There is this famous building in St. Petersburg where there are 4 titans holding the cornice of a building. And they're magnificent sculptures, and they look identical. So someone took a handheld 3D scanners and scanned them, and then superimposed the scans, and the deviations are like fraction of a millimeter.
Wow.
Yeah, and if you think, all right, well, this was a commissioned work, so somebody chiseled it. Yeah, those they are. If somebody chiseled them, first of all, there is no need to make them identical. You want to give them personality, right? And then even if you try to make them identical, you won't be able to.
Right.
But they're nearly identical because that's what that scan has revealed. So which means they were not chiseled, they were either cast or molded, or it's something else that's made look like a stone, but it's a stone on the surface.
What stone is that?
I think it's granite. It looks like granite.
Wow, that's incredible.
Yeah. So I mean, things that people walk by like daily.
Yeah.
Oh heck, in my hometown, I was walking. I was born in Smolensk, and I was walking to school through the fortress, and there was this earthwork next to this fortress that looked just like a mound to me. But recently, I looked at the satellite picture and like, oh my God, this looks like a star-shaped fortress that from the ground you cannot see. But these various hills, when you look at them from the from a satellite or from a drone, you could see a fortress. But I never knew it was there, and I walked past it to school like every day. And these are the same things we're talking about. We walk past them daily. We never question them, and then when we start questioning them, the narrative falls apart because it makes no sense.
Yeah, for sure. Are those the most fascinating sites and mysteries within St. Petersburg in Russia? Or
I think so. Yeah, the megalithic. There is this megalithic bathtub. Nobody knows who. I mean, they say it was made in the Urals and brought. Yeah. And once again, without the roads on horses, how?
Right.
The other thing that comes to mind, and this is not controversial. So they found ruins of cities in Siberia, and one of them is called Archaim, and that's the megalithic bathtub.
Wow.
Yeah.
Oh my God, dude.
Yeah, I mean, why, how, and it's in it's in the middle of a dump.
Yeah. A bathtub. It's like you can drown in that. I mean, you can drown standing up in that thing.
Yeah.
You can drown.
It just keeps going. I mean, there are ruins of megalithic walls around St. Petersburg that was this polygonal blocks. But what I was going to say, this in Siberia, they found this culture in one of the towns they called Archaim, and it's like a spiraling town that housed smiths and potters and all trades we can think of, and they found many of these identical sites throughout Siberia and Kazakhstan, and they date like thousands and thousands of years, maybe like 3,000 or 4,000 years. And recently we've been told there was nothing in Siberia, and now we find in these towns. So we don't know who those people were and why they left. We know that they burned their town and left, so it was like a deliberate destruction. Yeah, that's it.
That's it on the right there.
It's something new that's been discovered, and very few people talk about. But it's not just one town; it's a bunch of towns like that they're finding.
And that's Siberia.
And it's Siberia and Kazakhstan.
And so, but would Siberia have been under the ice sheet during the so 25,000 years ago? This is under ice.
Yes, sure.
Okay. So potentially just after, I guess, or at some interglacial period, this was in use by mankind.
Yeah.
Yeah.
And we know nothing about those people. I mean, what else we don't know?
Right.
Well, I don't know if you've heard about it. There is such thing as a Potomsky crater that doesn't look like anything I've ever seen before. And to me, it doesn't even look like a crater. It looks like an anthill, like giant anthill, except that it is giant. And if you look at the picture, you see trees look like very small in comparison. It's very unusual. I've never seen anything like it. It's deep in Siberia, not far from Lake Baikal, I believe. I don't know what it is. Maybe natural.
How does something like that even form?
Yeah, I've never seen anything like it anywhere. So whatever it is, it's unique.
Yeah.
And it does remind me of the little mounds that ants make on my patio every day.
Right.
Except this would need to be some mega ants to do it.
And what type of stone is it?
They say limestone with quartz.
Limestone. So you know what it could be? This is crazy. I was just talking to a guy who emailed me, and he's telling me about limestone and how it's used as a natural filtration system for water and how it like cleans water. I wonder if ancient humans potentially were using that to gather rainwater and to have it filtered down through somehow and to clean it and create drinking water.
Who knows? I mean,
or maybe not even rainwater, but I mean,
now that you mention it, we live on the surface of this planet, right?
Yeah.
So we don't know what's under the sea. We don't know what's under the ice. We don't know what's underground.
Right.
We think that the surface is it, but when you count the surface, the area is so much less than the area could be underground or under ice or underwater. So we know nothing of this planet. So chances are whatever we know is not just incomplete, it's also wrong.
Right.
I don't know where to stop wondering.
Yeah.
It's just so much to learn, so much to explore.
Yeah.
If we only, dared to. That's what we need to do and explore what's interesting.
Right. But there's nothing else like that naturally occurring that I've ever seen.
Not to my knowledge, not that I've seen.
No. I wish we had better relations with Russia right now. I'd love to go see some of this stuff.
Well, hopefully soon. Yeah.
Hopefully soon.
I'd like to go
it's
too.
going in that direction. Yeah.
I'm dying to go myself because I haven't been going for a while, when shit hit the fan with all of the wars and stuff. But yeah, it would be nice for all of us to go.
Yeah, for sure. Yeah.
Be able to comment on some of that stuff.
Right.
Because, I mentioned this, earthworks, ancient earthworks. There is ample evidence of prehistoric dikes and canals. Like Volga was connected to Don River, way before Stalin did it. And there are some dikes and walls that we call like snake walls that we don't know who's built, but they're like hundreds of kilometers long. But we're talking like mega structures, just piled earth, clearly, to direct water. But, who's done it? Who had the, like those, who had the technology to do it. God knows, because there's no record of it.
And how long does that thing go?
Hundreds of kilometers.
Wow.
Sometimes thousands of kilometers. Yeah.
Jesus. That's a lot of shoveling.
Yeah, it's in plain sight,
Yeah.
Anybody can see, but nobody asks questions. People drive by, walk by, and nobody is.
Right.
But when you think about it, you're like, really?
Right. Yep. Incredible. So many mysteries, so many things to dive into. This is why I made this channel. Right. Well, excellent, man. Well, what did we miss? This has been amazing. This has been a great chat. First off, can't thank you enough for the work that you've done on these artifacts. I've learned a ton through you and through your work on them, through your scientific approach to them. So thank you again, once again for. Yeah, it's been a lot of fun to work with you, and hopefully we can continue and continue to learn more. What did we miss? Anything on your mind?
No, I don't think. I really look forward to continuing this. I'm looking for an opportunity to do some on-site work in Egypt. So that would be interesting because that way we can learn some more. or for that matter, just anywhere.
Yeah.
Anywhere in the world, I think I'd like to take my nuclear instruments and to take measurements. So one way or the other, I'm going to do it.
Love it. Love it. Cool. How can people find you, follow your work?
Good question. I need to do something about it. I haven't thought about it, but
start an X account before we air this episode.
Yes, we need to do that.
Yeah. But you've got your website where you
yes,
where you've
Maximus.energy is my website. Yes.
Yep. And you've got the work on the vases there, and a lot of other work that you've done there.
Yeah, I maintain a blog there, and I post my ideas. So if you're curious to see what I think, and I have a lot of ideas on math, on physics. And I write a paper and I post it on my blog. And
cool. Love it. Well,
Thanks.
It's been amazing to chat with you, man. I really enjoyed it.
Thanks, Matt.
Yeah, for sure. I know it's not a long drive, but appreciate you braving the Florida traffic to get to me today.
Hopefully not the Florida snow, right?
Right. Exactly. Well, hopefully we'll do it again one day. We'll get another update, and we'll connect again one day, and we'll keep making progress on this vase topic.
Very good. Thanks.
All right. Love it.
Bye-bye.
Good stuff, man.